Okay, so welcome back. Let me say where we were on Monday, last Monday. So we had seen the definition of a subsequence. Okay, which was given an infinite sequence of numbers, which we usually denote n sub k. Okay, so this is like n1 less than n2, and continuing. Then we could, given a sequence xn, make a new sequence xnk, which was just the first term is the first term of the sequence here, second term of the subsequence is the n3, n2, and so on. Okay? And then we had proven a nice fact, right, which was given the monotone, which was called the monotone subsequence theorem. What this said was that any sequence has a monotone subsequence. Okay? And this was kind of this argument involving peaks. So these were terms of the sequence that were greater than or equal to any of the terms remaining or further on. And so either you could find infinitely many of those, that would give you a decreasing sequence, or the fact that there's only finitely many produces an increasing sequence. Okay? So I want to give a major consequence of this. Okay, so let me just recall also that we had the monotone convergence theorem. Okay, which was that a bounded monotonic sequence was convergent. Okay, so essentially putting these two together gives us our first main theorem about bounded subsets of the real line. So this is called Bolzano-Weierstrass theorem. Okay, which states that a bounded sequence of real numbers has a convergent subsequence. Okay, there are other ways that it's stated in the literature. If you just, Google Bolzano-Weierstrass theorem, it might be stated differently. It's going to be essentially the same idea of the proof and really the same statement. Okay, so let me just give you the proof, which is now quite easy. Because we did a lot of work in proving monotone convergence theorem as well as monotone subsequence theorem. Okay, so take xn. By MST, it has a monotone subsequence. Oh, sorry, I forgot to put that in here. Has a monotone subsequence. X sub nk. Okay? So by MCT, since xnk is bounded, right? We're assuming that xn is bounded. Then it's convergent. That's it. Bounded. This implies that the x and sub k's are convergent. Okay. So again, a good amount of work went into proving these two, but we get this as a simple consequence. So here's kind of a philosophy here. Okay. So this is essentially a finiteness property of bounded subsets of the real line. Okay? So, in some sense, they're acting like finite sets. Okay? So let me explain this. Well, so if S is contained in R as a finite subset, and we have a sequence which just goes into S, okay? So I'll just put it this way, F from N to S is a sequence. Then there is a convergent subsequence. Right? In fact, you could just make it constant, right? So there is a convergent constant subsequence. Right? Like imagine S is just, 0, 1, and 2, and we're looking at a sequence of numbers here. Well, there's going to be infinitely many, zeros, ones, or twos. You might not know what they are, right? But you certainly can't have finitely many of all of them. So you'll see some, say, infinite number of zeros, and then you just get the subsequence, just 0, 0, 0, and so on. Okay? So in particular, this fact holds. And now this is saying that if you just look at any bounded subset of the real line, it has the same property as a finite subset of the real line. So this is a pretty powerful idea. Maybe I'll just say a buzzword, which is compact sets in topology, which you can look up. It's a little different. So it's bounded isn't quite strong enough for the general statement. You also want it to be what's called closed, which you can think of as just like a closed interval, for example. Okay. So these are the sets which, again, like they're not finite sets, but for a lot of the properties that you might be interested in, they behave like them. Okay. Okay, so let me add one remark, which we've seen before, of course. Well, so a sequence can have convergent and divergent sequences as well, right? So the Bolzano-Weierstrass theorem is not saying that every subsequence converges, and it really doesn't tell you anything about where the subsequence is. You have to, if you want to show it converges, you have to find it yourself. Kind of convergent and divergent subsequences. Okay, so if I take the sequence -1, -1, -1, oops, -1, 1, -1, 1, and so on, then, well, of course I can look at the convergent sequence -1, -1, or 1, 1. But I could also just take a random sequence, which ends up looking like, -1, 1, 1, -1, 1. All good subsequences, but have, very different convergent or divergent behavior. Okay? So there is one case where you can where you can say a sort of converse here. So let me put this here. So take a bounded sequence. We did see before that if you had a convergent sequence, then every subsequence was convergent and the limit was the same. Okay? So in this case, we can now prove the converse of this, but we have to, you have to assume that every convergent subsequence converges. So let me just put this here. So if every convergent subsequence, and notice Bolzano-Weierstrass theorem is saying that there's at least one of these, of xn, converges to x, then the entire sequence has to converge to x. Okay? So note this is false for unbounded sequences. Right? So I could take, for example, the sequence 1, 2, 1, 3, 1, 4, etc. This certainly satisfies this criterion, right? Because there's a single, so there's not a single convergent subsequence, but maybe I'll just say this: every convergent subsequence converges to 1. It's just the constant subsequence. But of course, the sequence itself doesn't go to 1, right? So it's kind of remarkable that if these terms aren't going off to infinity, you would have to have the same convergence. Okay? So let me give you the proof. So let me first just make the bound explicit. So we're assuming that the xn's are all bounded by m for all n and n. Okay? And what we want is to assume that the xn does not approach x and derive a contradiction. Okay? And get a contradiction. Okay? So, since we know that the xn's approach x, there has to be some, epsilon, which is bigger than 0. I mean, this is just going to be the negation of the definition of convergence. Okay? And a subsequence so that x and k minus x is greater than or equal to epsilon naught, okay, for every k and n. Okay, so this is something that you get immediately from looking at the negation, right? So the negation of convergence says there's some epsilon naught, so that for any natural number you choose, there's some larger natural number where this holds, okay? So that just gives you your subsequence by taking these increasingly large natural numbers that have to satisfy the criterion that they're bounded away from epsilon naught, or bounded away from x by epsilon naught. Okay? So the xn's are bounded, which means that the subsequence is also bounded. Okay? So notice that this subsequence on its own, you don't know that it converges or not, right? You just got it from this fact that it's far away from x, but you have no idea whether it converges. On the other hand, there is a subsequence of that which is convergent by Bolzano-Weierstrass, okay? So there's the x and k has a subsequence, x sub n sub k sub l, too many letters here, which is convergent. By BWT, okay? By Bolzano-Weierstrass theorem. Okay, and since you're taking a subsequence of a subsequence, this is still just a subsequence of xn. And clearly it does not converge to the x, to x, right? So since the x sub n sub k sub l minus x is greater than or equal to epsilon naught for every L, we have to have that, so we have that does not converge. Okay, and that contradicts our assumption that every convergent subsequence converges to x. Okay, so that's the proof. Okay, so now, here, let me pull this up. So you might be thinking that we're pretty good at this point, right? So this is great. And all we have, we understand if we take a bounded sequence, we get this convergent subsequence. We even know where it converges to, right, by monotone convergence theorem. But we still need more machinery. Okay? And the reason is we want to understand, convergence of sequences where they're highly non-monotone. Okay, so to describe convergence of non-monotone sequences. Okay, so sequences that are oscillating back and forth, they don't have any, So what I mean is, well, certainly you can say, okay, there's a convergent subsequence. But that's not really what you want, right? You'd like to say that under other conditions, where it's still oscillating, we actually get a convergent sequence, all right? And what we don't want to do is go back to our previous theorem and check every single convergent subsequence, because that's a lot of subsequences to look at, okay? So you want a condition which kind of handles oscillating sequences and still guarantees convergence. Okay, so this is kind of a new major idea. So let me give you the definition. Okay, so we say a sequence x sub n is Cauchy if for every epsilon greater than 0, there exists some n and n, so it starts the same as convergence, okay? But then we say such that for every n and m, which are greater than or equal to n, and these are also natural numbers, we have that the x sub n minus the x sub m is less than epsilon. Okay? So notice it kind of feels like convergence, right? But there's absolutely no mention of a limit, right? We don't know, there's no x to kind of shoot for. You're only looking at comparing terms of the sequence. Okay, so this is kind of a tricky definition. Right? Because we usually measure, distance from xn to some target. Right? We know what we're kind of working with, some target x. And then you show that, x minus xn is less than epsilon for all n very large, and then we're happy, right? But here, we don't have something to shoot for, right? We're measuring, how far the sequence gets away from each other, right? So how far off, in terms of the sequence, are from each other. Okay, so in some sense you're trying to hit a moving target, right? You don't have this fixed x. The terms of your sequence are always moving as well, okay, as n increases. So here's some, basically the intuition, right, which is that for a Cauchy sequence, Cauchy sequence, the terms are eventually trapped epsilon away from each other. Right, notice that we're assuming it for every n and every m, okay? Epsilon away from each other. And that should imply convergence. That should imply convergence. Okay, so let me just draw the picture. So we have like maybe some first terms which we don't know anything about. Eventually, for a fixed epsilon, I look at x of n, where n is large, and I know that for any single m, right, for all m bigger than or equal to this n sub epsilon, the terms xn minus xm are less than epsilon. Okay, so again, this is just a term in the sequence, it's not the limit itself, okay, but I do know that every single xm is living in here, okay? But again, you still can't really find, you can never say that you've found the limit, you just have to compare terms of the sequence, okay? So let me do, first example, right? It's going to be the same example that we saw for convergence. Okay? So 1 over n is a Cauchy sequence. Okay, so let me just go through the details of showing this. Okay, so we get the idea of, what you now need to show for Cauchiness. All right, so for epsilon greater than 0, we want to show that 1 over n minus 1 over m is less than epsilon, okay? For n and m sufficiently large. Well, we have to just, do the algebra. 1 over n minus 1 over m, that's less than or equal to 1 over n plus 1 over m by the triangle inequality, okay? And each of these, by the Archimedean property, are less than epsilon over 2 for n m bigger than some n sub epsilon. Okay? So, you just have to, again, choose n sub epsilon greater than 2 over epsilon. Okay? So then this works, right? If I take this number greater than 2 over epsilon, then 1 over n plus 1 over m will be less than epsilon over 2 plus epsilon over 2, so we're happy. Okay? So what this means, again, this is kind of a harder calculation. But we never needed to guess a limit. Right? You didn't need to assume that this thing went to 0 and then proved it to show that it was convergent. You just do the calculation. Of course, at this point, we haven't shown, that this tells us anything. Eventually, we want to say that this will end up showing that this sequence is convergent. Okay, but we're not there yet. So let me do another example of something that's not Cauchy. Okay, so 1 plus minus 1 over n is not Cauchy. Okay, I'm just basically doing this example to write down the negation of what it means to be Cauchy. Okay, so we kind of have that. All right, so there exists some epsilon not greater than 0. This is the negation. For any n in the naturals, now there exists two things, so n and m greater than or equal to n, so that xn minus xm is greater than or equal to epsilon naught. Okay? So in this case, for n even, we have xn is 2, and for xn plus 1 is 0. Okay? So now, so the only difference is to show that a sequence is not Cauchy versus showing a sequence is not convergent is you need to find two things, right, rather than one. You have to find two elements nm instead of just finding one element n and comparing it to the limit. Okay? So xn is 2, xn plus 1 is 0. So if epsilon naught is 2, then, for all n in n, we can just take x, say, 2n and x 2n plus 1 contradict Cauchy. Okay, because they'll be 2 apart and they're larger terms than xn. So let me just give kind of this remark here. When you are trying to prove Cauchy, you cannot assume any relation between xn and xm. Okay, so you're not allowed to say, well, I'm just going to look at, xn and xn plus 1. That doesn't work. You have to do it for, any relation that you might think of, you should avoid, right? You're just trying to say, for large n and m, which have nothing to do with one another, they have to satisfy this criterion. Okay, so let me give the main application, or the reason why we look at Cauchy sequences. Okay, so here's the theorem, which is called Cauchy convergence criterion, which says a sequence converges if and only if it is Cauchy. Okay. So one direction I'm actually going to put on the homework. It's not too bad to show that if you take a convergent sequence, then it's going to satisfy the Cauchy criterion. It takes some more work to show the other way, right? So we want to show that if a sequence is Cauchy, we have to essentially find this limit which it converges towards. Okay, so we'll do this right now. Okay, so let xn be Cauchy. All right, and we want to show that it converges. So here, let me just tell you the strategy first before we prove this, okay? So here's the strategy. So the first thing is we want to show it's bounded. Okay, that's obviously a necessary criterion for it to be a convergent sequence. Okay, so we get from this so we want to get a subsequence which converges to some x. All right? Then we want to say that the entire sequence, the entire sequence converges to x as well. Okay? So show it's bounded, show it converges, or show a subsequence converges, and then show the whole thing converges. All right. So the first part is very similar to showing that a convergent sequence was bounded. All right? So xn Cauchy implies, say, that there exists some n in N so that xn minus xm is less than 1 for all n and m bigger than n. Okay? This is just the Cauchy criterion applied to epsilon being 1. So this is my epsilon here. All right, so what do I have here? Well, I fix some xn, where n is greater than or equal to m, or n, sorry. And then I know that every single xm is inside here. Okay, so it's inside xn plus 1, xn minus 1. All right, so now, and this is true, sorry, for all m greater than or equal to n. So now what's the general bound that we have? So the terms x sub n are bounded by the maximum of x1, x2, up through xn, and then xn plus 1. Maybe I should put, just to avoid working with positives and negatives, I'll just say put absolute values everywhere. Okay. Okay. So again, the sequence might do kind of, wild things at the beginning. But we know that eventually they're all going to be reasonably close to this x sub n. Okay? And then if x sub n is positive, we just, get this as an upper bound. If x sub n is negative, it might be this as the lower bound. But again, since we're taking absolute value, we're okay. Okay? So we have a bound in a similar fashion. Luckily, the second one is quite easy, right? Because, well, again, we did a lot of work to prove it, but by Bolzano-Weierstrass, we know that there exists some convergent subsequence. And again, I'm just going to say x is the limit. We don't have any idea what it is, but we know that there's subsequence which converges. Okay, and now we want to get something about the whole sequence. And this is really where we use the heart of the Cauchy criterion. Okay? So we want to bound x sub n minus x for n large. And you might think, well, we only know stuff about the subsequence, right? That's true. Okay, so we have to deduce it for all n large. And we only know stuff about, the x sub n sub k's minus x for k large. Okay? So now the trick is to use the Cauchy criterion to go between the sequence and its subsequence. Okay, so let me just write this out. If I have xn minus x, well, this is certainly equal to, for any terms, xn minus x sub nk plus x sub nk minus x. And then by triangle inequality, this is xn minus x sub nk plus x sub nk minus x. Okay? And now we see this is something. We can make this small by the Cauchy criterion. Right? This just has, these are two terms in my sequence. And this we can make small by convergence. Okay, so let me make this precise. Okay, but this is the main idea. So the Cauchy criterion is exactly the thing that lets you kind of interpolate between a sequence and its subsequences. All right, so let's do it. So let epsilon greater than 0. We know there exists some n and n, so that for all n m greater than or equal to n, xn minus xm is less than epsilon over 2. And there also exists some m in n, so that x sub nk minus x is less than epsilon over 2 for all k. Oh, maybe I'll just say for all nk greater than or equal to n. Okay? Turns out to be equivalent. Okay, so now take the max. So let P, sorry, had to go through my alphabet, is the max of n and m. Then, for all n greater than or equal to p, we have that xn minus x is less than or equal to xn minus x nk plus x sub nk minus x. And we've cooked it up, so since everything is greater than or equal to n and m, this is less than or equal to epsilon over 2. Oops. Less than epsilon over 2. Less than epsilon over 2, so the whole thing is less than epsilon. Okay? Okay, so that's the proof. So on Wednesday we'll see some applications of this. On Friday we'll probably see some more, this is called topology of the real line, and we might see also how you can use these Cauchy sequences to actually give a definition for the real numbers. So, okay, see you.